This is revision for OCR Gateway Physics, section P1D, Light and Lasers. In this section we'll cover Morse code, fibre optics and how they work using total internal reflection, lasers and an application of lasers in CD players. Light has been used throughout history to communicate, from lighting fires on the side of mountains and using those as beacons, to using lamps flashing on the decks of ships to send signals between ships, to fibre optics that we use today. In this picture here you can see somebody sending a signal from the deck of one ship to another by flashing a lamp, and the code that they would use to do that is this thing here, the Morse code. You can see that each letter of the alphabet can be represented by a flash of light, and one of these longer lines represents a long flash and the dot next to it represents a short flash. The code is called Morse code, and it can also be used to send messages electrically, and that's how the telegrams worked, which were like the first text messages, if you like, before the telephone was invented. And it was also used a lot during the First and Second World Wars to send messages by radio. One of the advantages of using light to communicate is that it's fast. Obviously your signal travels at the speed of light. To cover longer distances, the signals can be relayed, so one station will pick it up and then transmit it on again to the next station. And the signal, as we can see here in the Morse code example, would be a series of on and off signals, so a digital signal. This table shows us some advantages and some disadvantages of using different methods of communication, namely light, radio waves and electrical signals. Light is used in fibre optics, which we'll come on to in more detail later, but an example of that would be if you have Virgin TV or cable TV, then the signal that comes into your house is received via fibre optic cables which are laying under the footpath or under the road outside of your house. Radio waves, so this is what is used for TV and radio and to a degree mobile phones as well. And electrical signals, this is used if you have broadband internet through your home phone, so BT broadband, and it's also what's used in your landline if you have a landline at home. Okay, so first of all, using light and optical fibres, well, they're very fast. The information travels at the speed of light, and optical fibres can also carry a large amount of data quickly. The signal quality is very good over large distances. But the disadvantage is, in a lot of areas, the fibre optic cable isn't already present, so it has to be laid before it can be used, which is expensive. Radio communication doesn't require any cables, which is a big advantage of that and makes it very portable, and that's why it can be used for mobile technology. It's also fast because radio waves, like light waves, travel at the speed of light. A disadvantage is it's more easy to intercept, so it's more easy to eavesdrop on somebody else's signal, and over long distances the signal can be poor quality. The advantage of using electrical signal to send information is that the infrastructure is already in place. This is how information would be sent down a landline, so you'd make a phone call using a landline. Disadvantages is that the signal is sent more slowly than in fibre optics, and the signal quality can also be a bit poorer, and compared to radio communications it's not portable because you need cables. So moving on to talk specifically about optical fibres, this picture here shows a bundle of optical fibres, and this one here also shows a bundle of optical fibres, but for this one will be used for communication, so that's what might be laid underground. And this is what you might see on your Christmas tree or a lamp or something like that at home, so optical fibres used for decorative purposes. These two pictures here show how light travels along an optical fibre, so we can see perhaps a bit more clearly in this one than in this one how the light reflects off of the edges of the fibre, and here we can see how light can travel along one end, and even though the fibre is curved it can travel to the other end, and you can see light coming out there at the other end of the fibre. So on the next slide we're going to look at the physics behind this. Optical fibres rely on something called total internal reflection to work, and you may have done an experiment that looks something like this in one of your science lessons. Fibre optics use either light or infrared to send signals. But total internal reflection doesn't just happen for light and for infrared, it can actually happen for any wave. So let's have a look at what total internal reflection actually is. And in doing that, we're also going to have a recap of refraction. Let's look at this diagram here. In this diagram, we've got a ray of light being shone into a glass block. We're going to look at this point here, the interface between the air and the glass, this point at the edge of the glass block. When the light reaches this point, a small amount of it is reflected back into the glass block, but most of the light passes out of the glass block. It doesn't continue in the same direction, it's refracted slightly. This is because the air is less dense than the glass, so the light speeds up as it leaves the glass block. Okay, let's move on to this diagram down here. We've got exactly the same setup, but this time this angle here between the ray of light and this imaginary line at right angles to the glass block has been increased. So comparing it to this photograph, the angle between the light here and this imaginary line here has got slightly bigger. If this angle has been increased to a certain point, none of the light will actually be refracted out of the side of the block. All of it will either be reflected internally or will pass along the edge of the block, along here. Now this happens when this angle between the incident ray and the normal is equal to what we call the critical angle. The critical angle depends on the material through which the light is passing. For glass it's about 42 degrees. So this angle here, C, would need to be about 42 degrees to get this effect here, where none of the light is leaving the block from the side. If you keep increasing the angle between this incident ray and the normal line, so that this angle now becomes bigger than the critical angle, what happens is none of the light is refracted either out the side of the block or along the edge of the block. All of the light will be internally reflected. And this is a situation called total internal reflection. It just means all of the light is reflected back inside the block. So we can say that total internal reflection happens when this angle of incidence is greater than the critical angle, with the angle of incidence being this angle here, the angle between the incident ray and the reflected ray. This slide is for foundation tier only, and it shows some uses of lasers. So for example, laser eye surgery here, laser guided weapons, laser cutting, and for light shows. And we need to know that a laser produces a narrow beam of light of a single colour, or a monochromatic narrow beam of light. Okay, so this side is talking about the properties of laser light, and it's for higher tier students. Well, first of all, if we compare laser light to white light, we can look at these two diagrams here. This is an example of a white light source, and we can see that it produces light of different frequencies, so different colours, and that the light travels out from the source in all directions. By contrast, we've got a diagram showing light from a laser light source at the bottom here. The light is travelling in the same direction. Light of only one frequency, so one colour, is present, and all of these crests and troughs are aligned. So it looks like the waves are lined up. So how do we describe this? Well, if you're going to learn a phrase about lasers, this is a good one to learn. Lasers produce an intense and coherent beam of light. So what does that mean? Intense means that a lot of light falls on one area, and that's to do with the idea that the waves don't spread out in all directions. Sorry, the light doesn't spread out in all directions. The light travels in the same direction, and this links into this keyword here, low divergence. They don't diverge, they don't spread out. So the light doesn't spread out, the light waves don't spread out. And that's to do with how the light is produced inside a laser, which we won't go into here. Now this next word, coherent, is linked to these two descriptions here. Same frequency and in phase. Same frequency means that all the light is the same colour. Only one frequency of light is present, so only one colour of light is present. Another word for that is monochromatic, which I've just put in here. Monochromatic, same colour. And that's due to the fact that all of the light is the same frequency. In phase means that all of the crests and all of the troughs are aligned, as shown in this diagram here. The easiest way to describe in phase, if you're asked a question on it, is actually to draw two waves that look like this, and you will get marks for that. This picture here actually shows the bottom surface of a CD, and this image is taken using an electron microscope. You can see these kind of pits here, some longer, some shorter, and this is actually the way that information is stored on the bottom of a CD. It's stored as a series of pits, sort of raised bits and lowered bits, and that forms a code for whatever is stored on the CD. So it must be a digital signal. Remember, our digital signal is a series of ones and zeros, and the information on the surface of a CD is a series of bumps. Now, those bumps are read using a laser, so if you look inside a CD player, you'll always see something like this, and this is the source and the reader inside here. So a laser beam will be shone from there onto the bottom surface of the CD. The reflection will bounce back, will be reflected back, and by the way that the reflection appears, the CD player will be able to tell whether it's been reflected off a bump or off of a flat surface, so off a raised bit or off of the flat bit. And from that it will be able to read this code, and then the circuitry inside there will be able to interpret that code, and you'll be able to get the information off of the CD. One CD will contain billions of these pits, and if you've got a Blu-ray player at home, or most CDs use red laser light, but if you happen to have a Blu-ray player at home, that's a CD that uses blue laser light, and the reason for that is that blue light has a higher frequency than red light, so the wavelength, the blue wave, is more squashed together, if you like, than a red light wave. And so because the wavelength is much shorter, much more information can be stored on the CD, because the bumps can be a lot smaller and still be read. And that's it for section D.